So what we're going to do is we're just going to finish the chapter of this Engel book. And then we'll not meet on Friday there. I just have some deadline to pass on. And I will make available chapter 2 and chapter 4. Okay. So I will give that time to you to at least find the topic for your review paper and the article critic. So even though we're not going to meet, you have some stuff to do during that time. So in our last discussion about chapter 2, the petrochemical measurements, we talk about absorbance, we talk about luminescence emission, okay? We talk about the, if you're going to recall, so we talk about emission, absorbance, luminescence, okay? Molecular and atomic fluorescence, okay? And we end up with this, what we call measurement of luminescence region. So what we're going to talk about today is scattering measurement, and then some terms that we always use interchangeably. Okay, so when we're talking about this scattering experiment, so we're talking about radiation from an external source. Okay, that is, we could say, affected by the sample. So the way that you look at it, when your light, okay, or radiation pass through the sample, okay, it is scattered by the sample. So I think we have some discussion of it before about this scattering in the previous, I'm not sure if it's last week, okay, but we have mentioned about scattering during that time, okay. So we could say in addition to light being absorbed by the sample, it can also be scattered, okay, by the sample. So the intensity, the frequency, and the angular distribution of scattered radiation can be used in spectral chemical methods. Okay, so remember the intensity, the frequency, and angular distribution of the scattering, it can be used in spectrochemical method. So if we're going to look at this, okay, we will allot some time on molecular scattering in one of the future discussions. Okay, so usually if we have particles that are smaller than the wavelength of the incident light radiation, it can scatter that radiation elastically without a change in its energy. So that's the example of what we had, the so-called Rayleigh scattering. Okay, so if you remember, Rayleigh scattering is typically occurs with atoms or molecules. So it's a phenomenon when the size of the scattering particle is much smaller, okay, than the wavelength of the incident light. So one explanation of why the sky is blue is scattering, okay? And it also, we could say the reason behind, I don't know if you see it, that what's the color that you see when you look at the sunset? Ano usually kulay ng sunset? Anyone? Okay, orange, sometimes red. So that's another example of what we call Rayleigh scattering. So Rayleigh scattering, scattered radiation occurs in all directions from the scattering particles. Okay, so we could say in terms of the particle size, uh, the particles, the scattering particles are much smaller than the wavelength of the light. Okay, so we could say in terms of wavelength dependence, the intensity of scattering is what? Inversely proportional to the fourth power of the wavelength. So that we could say the relationship of uh, wavelength with the scattering. Okay, so the intensity of scattering is inversely proportional to the fourth power of this what we call wavelength. Okay, now there are also scattering from different size, like this device scattering or device scattering. So if you have a scattering that takes place from larger particles with dimensions on the order of the wavelength of the incident radiation, that is what we call device scattering. Okay, so here the scattered radiation is the same, okay, as the frequency of the here the scattered radiation is the same frequency as the what we call is incident radiation, but the angular distribution of the scattered radiation is not uniform, unlike the Rayleigh scattering. Okay, so if we have this what we call device scattering, usually that what we call type of scattering that occurs when the size of the scattering particles is comparable to the wavelength, okay, to the size of the wavelength. So we could say it's almost the same as the wavelength size. Okay, so this is we could say very different from the what we call the Rayleigh scattering. Okay, so in terms of the particle size, they are comparable to the size of the wavelength. So in terms of the wavelength dependence, what would be the relationship here? So we could say the scattering is less dependent on the wavelength, unlike or compared to the Rayleigh scattering. So we have radiation, Rayleigh scattering, okay, device scattering. So I try to what we call differentiate them from one another. So I think the difference now between the two is the size, okay, the dimensions of this what we call particle. One is smaller than the wavelength of light, okay, or incident light, and the other one is comparable. Now we have also mis-scattering. We encountered this already before. So mis-scattering, it occurs when the scattering from much larger particles. So large particle scattering, so we could say D by or me, they can be used to what we call determine the particle sizes, and it's important in turbidometry and mesallometry, where you have suspended particles, which are the scatterers. But if you're going to look at the mis-scattering, it occurs when the size of this scattering particles is similar to the wavelength of the incident light. And if you're going to look at this one, the mis-scattering, that is the, may term tayo dyan, general form of scattering that is applied to a wide range of particle sizes. And it's commonly observed in the conditions between Rayleigh and device scattering. Okay? So in terms of the particle size, just like the dBi, it is the same as the wavelength of the light. Okay. And in terms of the wavelength dependence, we could say the my scattering or mis-scattering occur for a wide range of wavelength, and it's not strongly dependent on the fourth power of the wavelength as in Rayleigh scattering. Okay, so it's almost, we could say, close to dBi in terms of size. Now, the only difference we could say in terms of the wavelength dependence, mis-scattering, they're not as strongly dependent on the fourth power. The dBi scattering, they're less dependent on the wavelength compared to this Rayleigh scattering. Okay, so we could say turbidimetry and nephelometry, that's where you have suspended particles. They are the ones that do the scattering here. Okay. Now, another term that we have in this scattering is this so-called Brillouin scattering. So, what's the difference of this scattering compared to the previous one? Anyone? So, the previous one that we discussed, all of them are what? Elastic scattering. Now, these two, Brillouin and Raman, they are both, we could say, inelastic. Now, when we talk about forms of inelastic scattering, which involve a change in the frequency of the incident radiation, we can talk about the two of them. Okay, but the main difference is the Brillouin scattering results from reflection of radiant energy waves by thermal sound waves. So they have a special, we could say, characteristic. Okay, special, we could say, form, because this is related to the interaction of light with, what could be the other term for the thermal sound waves? Acoustic phonon in a given material. So it looks at the interaction, okay, of light with acoustic phonons in a material. So reflection of radiant energy waves by the thermal sound waves. So it results, okay, in the scattering of light due to the presence of acoustic waves. So what's that acoustic wave? Usually the thermal sound wave. Okay, so leading to frequency shift in the scattered light. So it's the same way with the Raman, what we call the scattering. It also looks at the frequency shift. Okay, what Raman scattering involves is the gain and loss of a vibrational quantum of energy by molecules. And both scattering signal here is proportional to the incident radiant power. Now, in terms of particle size, what do you think? Do you think the particle size has a direct effect on this scattering? Because the three scattering that we have mentioned, dBi, me, okay, and Rayleigh, more or less, okay, there's a relationship between the size of the particles. But here, if you're going to look at the particle size, the Brillouin scattering is not directly associated with the size of the scattering particles. Instead, it is related to the acoustic wave. Okay. And if we're going to look at the wavelength dependence here, the frequency shift that you have in the Brillouin scattering is influenced by the speed of sound. Kasi acoustic nga eh. Okay? In the material, and it's not proportional to the wavelength of the light. So if we're going to summarize the 5, how are we going to summarize it? So Rayleigh Anong mai-associate natin sa Rayleigh? Small particles. And then D by, we could say particle size of the wavelength. Then me or my scattering is more or less the general case. And Rayleigh scattering involves interaction of light with acoustic phonons in a given material. So that's the difference between these what we call scattering. And if we're going to look at this, usually, now that we know the different light interaction with the matter, okay, absorbance, emission, luminescence, and scattering. So the next thing that we're going to do is to select what optical information are we going to use, okay? So in a given analytical procedure, the selection step allows us to separate the analyte optical signal from a majority of the potential interfering signals. Okay? So the vast majority of the analytical techniques select the desired information based only on its wavelength. So it's wavelength selection, the one that we're looking at. So if we sort out all the optical information that might be produced in the encoding step, if we remember, that's the major step that you have in spectrochemical measurement. Okay, so the selection process, it's not perfect. However, and we must be aware that there are limitations of the instrument and components used. The vast majority of our analytical techniques select the desired information based only on its wavelength. And as we go on, we could see that there are many additional criteria which we can employ to improve selectivity. Okay, so it depends, the use of time, discrimination, the position discrimination, polarization, multidimensional information, and chemical selectivity. Those are just few possibilities. But the most important one is selection of the wavelength. Okay, so that is what we call the selection of the wavelength. So if we're going to look at most of the optical instrument that we have, we could say this is the instrumentation that we can find. Okay, instrumentation, we're talking about spatial dispersion and detection of the optical signals. So if you're going to look at this, okay, what is the first thing that you need to have? Okay, what do you think is the most important part here?
Yung light source po. Ay.
Okay, so usually, ito. Pag wala yan, walang silbi yung iba. Okay, so we could say the radiation here is the most important part. Okay, if we're going to look at this, some of the radiation from the spectrochemical encoder enters what? The entrance slit. So when we go to the next chapter, we look at the optical component. Okay, you will see that this has different types depending on the optical instrumentation that you're going to use. But as I've told you, what happened, some of the radiation from the spectrochemical encoder or your light source enters the entrance slit and strikes the dispersion element. So if you're going to look at this, this is your spectrochemical encoder. So we could say encoder kasi i-encode niya through the light source kung ano yung hinahanap mo. So it passed through the entrance slit and then it passed through a dispersion element. Okay, so the dispersion element and the image transfer system cause each wavelength to strike a different position in the focal plane. So where's this what we call different photo detector configurations that can be used. So in the focal plane, you can have an aperture that has a photographic plate or film or array detector. I'm not sure if you heard the word PDA, photodiode array. Okay. And then you can also have another exit slit, or we could say if you have an entrance slit, you have an exit slit. And once it exits, you have the what we call a photo detector. Or you have some exit slits where you have what we call photo detectors. Okay, so according to the photo detector's configuration, various names were given to these optical devices. Okay, so usually if we're going to look at this, what do you think is the most common dispersion device that we use?
Yung grating po ba, sir? Diffraction grating.
Okay, that's one. Pero ano na tawag natin ngayon doon? Yan yung tinatawag natin monochromator. And we can also have a dispersion device na instead na mono, we can also have what we call polychromator if there's more than one. Okay? So the next thing that we're going to do, as I mentioned, various names given to this what we call optical device. So ito, i-differentiate natin bawat isa. So all of them has what? Common root word. Spectral. And what we're going to do is we differentiate each of them. So spectrograph, spectroscope, spectrometer, and then if you go later on, okay, meron pa tayong spectrophotometer at yung photometer. So how do we differentiate one from the other? So it says here, if you have a spectrograph, you have a large aperture in the focal plane. So if you're going to look at this, ito yung focal plane mo, meron ka diyang aperture ito. Okay? And what happened, it allows a wide range of wavelengths to strike a spatially sensitive detector such as a photographic plate. Okay? So in recent years, they used to have this what we call video type detectors that becomes what available for this so-called spectrograph. So instead of a film, they have this what we call the video type detectors. And these detectors are usually an array of a large number of closely spaced miniature photoelectric detectors. So if you're going to look at your what we call things here, if we go back there, so if you have this aperture here, okay, the plate, so you have some sort of this array of the detector. It's closely spaced miniature photoelectric detector. So they have the advantage that the spectrum can be obtained immediately without the time required for film development for obtaining the density of the lines recorded and so on. So if we're going to look at the function of the spectrograph, okay, so usually we could say it's an optical instrument used to record and analyze spectra. So it disperses light into the component wavelength and records the resulting spectrum on a detector. So if you're going to look at the components, it has a slit that allow the light to go in, a dispersive element like prism, diffraction grating, and the detector to capture the dispersed light. So I think what you have here is like a graph, photograph. Okay, that's why because you have this what we call photographic plate. Now, how is it different from spectroscope? I'm not sure if we did this in Chem. Okay, so usually this is spectroscope. It's like a telescope. It's just like a triangle. And then what you do, this is your eye. So you put in one of the lamps of an element. And then on this side, you're going to look at this, what we call line spectra. Yan yung spectroscope. It's a device that allows, okay, a visual observation of the spectrum. Meron ba tayo niyan sa physics ginamit?
Yes po, sir. Merong yung Physics 23. May ganan kaming excerpt po.
Ay, oo nga, optics yun, di ba? Siguro nga doon, parang yung, it can be black or it can be gray. Gray yung sturdy, yung black parang plastic. So yung isang side doon sa lamp, sa element lamp, tapos yung isang tingin mo, titingnan mo yung spectra, tapos titingnan mo ano yung nano wavelength. Anong wavelength nagkakaroon ng line spectra. So it's a visual observation of the spectrum. Okay? It is a spectrograph that uses a viewing screen for observing the spectrum in the focal plane. So unlike the spectrograph, parang nare-record niya, ito as is, in real time. Pag hindi mo natin, pag tinanggal mo yung light source, wala ka nang makikita sa spectroscope. Okay? And then we have the spectrometer. Okay? Or if we're going to look also in terms of the function of the spectroscope, this is just a general term for any instrument that observes or analyze spectra. So look at the difference of this with the spectrograph. One record, this one just observed. But both you can analyze the spectra that you can get out of them. So it can refer to a simple handheld device for qualitative spectral analysis or to a more complex instrument like the spectrograph. So we could say spectroscope, that's the one that you can get in real time. Spectrograph, pag na-record mo siya. Okay? And the components that you have here in the spectroscope is just as simple as the prism or the diffraction grating for diffraction and an eyepiece for you to observe the direct observation. So wala kang detector. Okay? Kasi yung detector, yun yung nagre-record eh. So ang ano mo lang, na-observe mo lang siya. Okay? Kasi you can only get it in real time. Now, in terms of this spectrometer, if we're going to look at this, I think this is the one that is usually commonly used. Okay? A spectrochemical instrument that is widely, we could say, used or employed, a monochromator or a polychromator in conjunction with photoelectric detection. Okay? So, meron kang either monochromator or polychromator. So, if you're going to look at this, there's a mono or polychromator here. And the photoelectric detector that you have there is placed outside the exit slit. So it could be this one. Okay. Now, if you have more, so you could say that is what? A polychromator. So what happened here? Okay. Those polychromators in conjunction with the photoelectric detector or photodetector of the isolated wavelength band. Okay, so if a polychromator is employed, we could say separate detector for each exit slit. So if it's a polychromator, so there's an exit slit for a particular wavelength, another one for another wavelength, and then another one for another wavelength, and each of them has photodetectors. Okay, so if you apply a photodetector here with a separate photodetector for each exit slit, we can call the instrument as the direct reading spectrometer. Okay? Pag more than one na siya, we have a direct reading. Now, some spectrometers, they use optical components to sweep the spectrum quite rapidly across a single exit slit. So yan yung nag-i-scan ka. Okay? You sweep, okay, what we call across an exit slit. And if you're going to look at the spectrometer, we could say that's a broader term that encompasses both the spectrograph and the spectroscope. Okay, it refers to an instrument used to measure the properties of light over a specific portion of the electromagnetic spectrum. But the way that we have right now, usually mga scanning na yung ano natin spectrometer. Okay, so the component that you have here, the dispersive element, okay, monochromator or polychromator, and a detector that observes the resulting spectrum. Okay, so just to emphasize, if you have a monochromator, your exit slit is about the same size as the entrance slit. So kung ano yung size mo dito ng slit, same size also dito sa exit slit. Okay? So what you do is just isolate a small band of wavelength from all the wavelengths that strike the focal point. And usually, if it's in what we call absorbance, kung ano yung ano dito, the same thing yung makukuha mong wavelength dito. Now, if it's emission, well, it depends. Okay, but the exit slit should be the same size. Now, if the focal plane contains multiple exit slits of the several wavelengths, bands can be isolated simultaneously. So we could say the wavelength selector there is a polychromator. Now, you also have a special type of monochromator that is what? Nagro-rotate siya. You can rotate the dispersing element. So one wavelength band at a time. Okay? So one wavelength band at a time is isolated, and then different wavelength bands can be selected sequentially by rotating dispersion elements. So this brings the new band into the proper orientation so that it will pass through the exit slit. Okay? Now, how is this different from this spectrophotometer? Have you used them before interchangeably? I think the commonly one that we have is spectrometer or spectrophotometer. But how do they differ from one another? So, if we're going to look at the definition here from the book of what a spectrophotometer is, okay, it's an instrument similar to the spectrometer, except that it allows, okay, the ratio of the radiant power of two beams to be obtained. And that is a requirement for absorption spectroscopy. So what do you think is measured here? The ratio of the radiant power, okay? And to determine what is really measured here, we have to go to this one, definition. Photometer. Okay? So if you have a photometer, it's a spectrochemical instrument which uses an optical filter for wavelength selection in conjunction with photoelectric detection. So ano sa tingin nyo yung minimeasure ng photometer? Anyone? If we go here at the beginning, kung ano yung tinitingnan natin. What do we usually look when we try to look at the optical information? Ano yung tinitingnan natin? Anyone? At the beginning, what do we usually look?
Yung peak wavelength po kung saan peak ma-absorb or transmit yung analyte.
Okay. So usually what we're trying to look at this one is to determine the frequency, intensity. Okay. So those are just some of the stuff that we look when we have this what we call optical measurement. Okay, so we look at the signals in terms of change in frequency or in terms of intensity. Now, what the photometer give us usually is a measurement of the intensity of light. And what measures the intensity of light? Aling part dito? Anyone? Although we could say the photometer, light is only one of the optical properties that it measures. It can also measure other optical properties. And because of that, you can use this for what? Quantitative analysis. And the main important component of photometer, ano sa tingin nyo? Alin yung major component ng photometer dito? Light will always be there, but I think the important one is a photodetector and a way to measure the amount of light or whatever optical property that you have there in the detector. You measure the amount of light falling on the detector. So you have a system, okay, to measure the amount of light that falls on the detector. That's why if you combine this photometer with a spectrometer, ito yung meron ka. Spectrophotometer. Kasi ang ano na dito, meron ng ratio of radiant power of 2 bins to be obtained. So, spectrophotometer falls under spectrometer. Specific type siya ng spectrometer that measures the intensity of light at different wavelength. At yan yung tawag, ang dapat na tawag natin doon sa instrument na ginagamit natin. Okay, it's not spectrometer, it's really a spectrophotometer. So if you're going to look at the components of this, andyan yung light source, andyan yung dispersive element, andyan yung sample holder, okay? And then you have what? Detector. And it can measure not only absorption, it can measure transmission or reflection. So I don't know if you learned something new about spectrograph, spectroscope, spectrometer, spectrophotometer, and photometer. Maybe our use of this term is usually exclusive for chemistry. But if you're going to look at the application, sa tingin niyo, saan ginagamit yung spectrograph? Anong other field ng science useful yung spectroscopy? Anyone? Saan pa ginagamit yung light to study matter? Sa chemistry lang ba yan? Physics? Masyadong malapit. Saan pa? Medicine? Do you agree with this? Maybe you have a telescope to look at it, but sometimes you look at the spectrograph. Remember Armstrong? Ano yung pinag-aralan niya? I think that tapos na ba yung quiz? Yeah, tapos na yung quiz, di ba? So pwede na ako magsalita. So ano pinag-aralan ni Armstrong? You name a unit of length after him, but what he really studied that is related to spectroscopy. Di ba yung sun? And he detected what? Ano yung dinetect niya? Hydrogen. Na-detect niya yung line ng hydrogen. Pero, Armstrong line ba tawag doon? Anong tawag doon? If you recall your Gen Chem, you remember this? Balmer's line? Si Armstrong naka-discover, pero that line was named after another one, Balmer. So if you're going to look at spectrograph, its main application is in astronomy for studying celestial objects, analyzing their composition, and determining physical properties based on emitted or absorbed light spectra. Kasi hindi mo naman pwedeng i-monitor siya in real time. So what you do is you photograph them and out of that try to analyze what it has. Spectroscope. Maybe ang use niyan dyan yung sa experiment. Qualitative analysis of chemical substances. So you look at the patterns and the colors of the spectra. Okay, and that's why you have this handheld spectroscope for educational purposes. Now, spectrometer, it has a widely application in different scientific disciplines. In chemistry, we can use it to analyze molecular structure. In physics, they measure the properties of light. In environmental science, they assess air or water based on the absorption or emission spectra. Spectrophotometer, ito yung ginagamit natin sa chemistry, sa biochem, and sa biology for quantitative analysis. So you either measure the absorbance or transmittance of a light by a sample and aiding the concentration determination of the solution. Now, photometer, You use it to measure light intensity in various fields. You can use it in astronomy. It determines the brightness of the stars. In environmental monitoring, they measure the ambient light levels. In photography, they assist in the exposure control. So those are, we could say, the different terms. Although, if we're going to look at this in the summary, okay, spectroscope is a general term for instrument that observes spectra. Spectrometer is the broader term encompassing instrument used to measure the properties of light. Okay? Yung spectrograph at spectrophotometer, there's specific types of spectrometer. Yung spectrograph nagpo-focus, okay, sa, saan na ba yung notes ko? Oh, yung spectrophotometer focusing on the quantitative measurements of light intensity, while the spectrograph is more on photographic plate. So yung photometer, it measures light intensity without spectral resolution. At meron pang huli dyan. Okay? Yung tinatawag nating interferometer. Now, interferometers, unlike everything that has dispersive devices, they don't have dispersive devices. Okay? So they are non-dispersive devices in which constructive and destructive interference of light waves can be used to obtain spectral information. So they use interference of light waves to make precise measurements, such as the determination of wavelength or testing optical instruments. Okay, so usually what we have here, it involves the use of 2 or more light paths. And interference between the beam. So which instrument do you think use interferometer? Anyone? You heard this already? Or another new term for you? Naawa na ako, puro new term tayo every time we meet, because these terms are really what we call the commonly used term in spectroscopy. So are you familiar? Is this the first time you heard interferometer? Destructive and non-destructive waves. Anyone has an idea kung saan instrument ginagamit to? Please. Hindi niyo to na ano sa 137? At least for those UP graduates? Anyone? Any guess? IR. So usually there are 2 types of this, what we call interferometer that you use. Okay? Yung tinatawag na Michelson interferometer. At yung isa ay yung tinatawag na Fabry-Perot interferometer. Have you heard this term? At least I think the most common one of them is the Michelson interferometer. So both of them are what we call types of optical interferometer. So the difference that they have, we could say, is in the design. Okay. So in terms of the design, one of them uses made up of what we call two partially reflecting parallel mirrors separated by small distance. So the Fabry-Perot, they have two partially reflecting parallel mirrors separated by small distance. So the light enters on one mirror, it undergoes multiple reflections between the mirrors and then exits through the other mirror. So it creates like a multiple beam that interfere with one another, producing a complex interference. So remember, we're looking light interference here if we have an interferometer. Now, the other common one, they use what we call, I don't know if you heard the term, beam splitter. So it is what it is. It split the light beam. Okay? So what we do, it divides the incoming light beam into two perpendicular beams. So one beam travels to a fixed mirror, while the other beam goes to this what we call movable mirror. And then the two beams will combine at the beam splitter, and you're going to observe what we call interference. So that's the difference that they have in terms of what we call design. So in terms of the interference pattern, so the Fabry-Perot, they produce multiple interference patterns known as fringes due to the multiple internal reflections between the mirror. And each set of these fringes corresponds to a specific wavelength, creating a series of narrow peaks in the interference spectrum. Now, Michelson, on the other hand, creates interference fringes that result from the interference between the two beams. So the fringes are observed as alternating bright and dark bands, and their visibility can be adjusted by changing the path difference between the two beams. Okay? So yun yung common sa what we call sa dalawang to, interferometer. So Michelson is the simpler one in design, and the most commonly used. Fabry-Perot, they are more complex if they have multiple internal reflections. Okay, so yung pinaka-common, I think the one that I use is usually the Michelson one. So you can only see them in IR. Now you can use also interferometer in astronomy. It usually enhances resolution in telescopes. In metrology, it measures length accuracy. In physics, it assesses optical components and explore wave traffic. Okay? So, now that we have these different ways that we can get from this instrumentation, okay? The next thing that we're going to look at is the optical signal measurement. But before that, okay, I would like to remind everyone that these things that we have right now, before it's really the what we call analog type, but with the advent of computer, so everything has gone digital. Unless you have the old thing there, because I remember when I was teaching 137.1, we don't dispose the old one because we want to see the students how the parts look like. So we just leave it open, and we ask the students, so what do you call this, what we call parts of the spectrophotometer. But I don't know if it's still being done right now. Okay? Kasi here, most of our spectrophotometer, we don't need cover. So sometimes we need it without a cover. There we need to cover. Why? What's the number one enemy of optical instrument, especially in the Philippines? Dust. That's true. It's the dust. Humidity kaya pa eh, pero yung dust medyo hindi na. And the combination of humidity and dust, that's really worse, makes it worse. Okay? So, in terms of this, what we call optical signal measurement, okay? So all the spectrochemical techniques that operate in the UV, visible, and IR regions of the spectrum, we could say employ similar instrumental components as what we have seen here in this black diagram. Almost all of them are just the same. Okay. The elements that they have are the same. Light source. The only one that makes it different is what light source that you have. One has a what's called a tungsten lamp. One can have a laser. One can have an arc lamp. Okay. But if you're going to look at this black diagram, we could say they employ similar instrumental components as mentioned there. And the major instrumental differences between the emission, photoluminescence, absorption techniques occurs in the arrangement and type of the sample introduction system, encoding system, and information selection system. Okay. So there's a specific transducer and signal processing devices that's used in various regions of the spectrum, and we will discuss about that on the next chapter. Okay. So if you're going to, we could say, look at this, maybe this one. So the radiant power monitor. So the radiant power monitor provides, okay, a numerical readout that is related to the radiant power. So the number of photons per second or what impinge on the transducer. So you have the light here, okay? So you have here, you impinge this on the transducer. So there's a way for it to be processed, okay? And whatever the power that you have here, the radiant power, it could provide some sort of relationship to the readout system that you have. Okay, so if you're going to look at this transducer, there are specific transducer and signal processing device that is used. But for now, we just look at how the analytical signal is extracted from the readout data in spectrochemical method. So for instance here, you rarely have a direct, we could say, reading in spectrochemical measurement. Usually hindi siya direct. Okay, you cannot directly obtain it directly. So for instance, if you have emission and chemiluminescence, the technique that the signal that you have that's defined as the signal to be displayed by the readout device due to only emission of the analyte. So we can have this as the emission, okay, and we presume that the emission is directly related to the radiant power of the emission. Okay, and similarly, we could look at the analytical signal in photoluminescence technique. So we have here the luminescence, and this is measured signal only due to radiationally produced emission of the analyte. So we just can put a relationship of what is emitted or what is luminescent based on the what we call radiant power that we have there. Now, in terms of the absorbance, okay, we could say that the signal there is due only to the absorption of the radiation by the sample, the analyzed species that you're analyzing. Okay. Now, you have to take into consideration that there are, we could say, background signals that register on the readout device. So what does this mean? If you have the presence of this extraneous signal, okay, such as the signal, let's say, from your concomitant, from your sample cell, okay, the room light. So what do you need to do? How do you eliminate this? The dark signal and the background signal. Ano gagawin mo? What do you usually do? Whenever you do the absorbance, what's the first reading that you do? Anyone? You get the blank. Okay. So the blank represents all of this. So what you do with the blank, there's another term for the blank in some of the instrument. Like this morning, I'm teaching my colleague because I said, oh, we have a new toy. It's much faster than the old one. Yeah, where's the blank? That's the blank, 0. Oh. Okay. So if you're going to look at this background or extraneous signal, there's usually, we could say, 2 primary sources. The dark signal. So that's the signal present when no radiation is impinged on the transducer. And the other one is the background signal due to the background radiation that strikes the transducer. So whether it is absorption, emission, I don't know with luminescence, I have limited experience on that. And even the Raman, we usually have this what we call dark background. Okay. So the background radiation is composed of radiation from all sources other than the desired optical phenomenon from the analyte. So our definition of the blank, everything in the sample except the analyte. So any optical signal that you get in everything in the sample except the analyte, if you do the blank, you 0 it. So any signal that you get after that is due directly to the analyte that you're looking for. Okay, so you can look at the instrumentation for emission like this one. So if you're going to recall your excitation source here, if you're going to look at our block diagram at the beginning, that is your encoder, right? Now, usually the excitation, that's the one that puts your sample from the ground state to what we call the excited state. So any emission that results from the excitation of the species by a flame, plasma, a chemical reaction encodes the concentration of the analyte as the radiant power of the emission. And in some spectrochemical methods, the excitation source and sample container are integral units as the nebulizer or the burner that we use in AAS.
Recording in progress.
What's that? And the reaction cell that is used in what we call the chemiluminescence. So in AAS, your sample container is integrated with your nebulizer and it goes directly to your flame. Now the wavelength selector, that is your information. Okay, so if you're going to look at this, So emission and chemiluminescence or the photoluminescence spectral here, as you look at this, okay, so your radiation source that you have here, that is your encoder. And then you select an excitation and then at a particular point, you're going to collect it. Okay, and usually what's the orientation here? If you have a photoluminescence or what we call an emission, usually you collect the emission at a 90-degree angle, so you can have a T configuration or an L configuration. So that's one of the difference, I think, in terms of this instrumentation. You don't get it directly because it will burn. So what you do is you let it excite and then you observe the view 90-degree angle. So if you're going to look at the total analytical signal that you get from luminescence, so we can do it like this one. ETL is equals to EL plus EE and EBK. So what are these? What do you think is this one? That's your analyte luminescence signal. And this one is your thermal emission. And this one is, what do you think is this one? The background, or we could say the blank. And if you're going to look at this, what we call blank, so this could be due to the dark, the background. So mostly this is the blank. And then east is the scattering. And this one is the background luminescence. Now, we can also do it in terms of the emission, like we have EE equals to ETE plus or minus EBK. So if you're going to look at this, the emission that you have there, usually it encompasses of different stuff. Okay. So the analyte luminescence that we have there, the signal can be only obtained between two measurements. Only if the analyte emission signal is small compared to the what we call luminescence signal, which is often the case. So if the analyte emission signal significant subtraction of the blank signal give a measured analyte luminescence that differs from it. Okay, but usually to obtain the true analyte luminescence, your emission luminescence, we could say, can be added to EE, where when EE is significant, the excitation source must be turned off, then the two measurements of ETE and EBK are made to obtain EE. So you have to take into consideration the other, what we call signal. So you subtract, okay, the emission signal from the emission luminescence, it gives the true analyte luminescence signal. Now, in some cases, you can eliminate the measured contributions of the analyte emission optically or electronically. But the thing right now, everything is, we could say, advanced. Noon, mano-mano mong anuhin yan eh, kukunin mo yung talagang signal niya. Okay? So if the excitation source is modulated or AC current, application is used, your AC luminescence signal can be distinguished from the emission signal that you have. So the only thing that you do is blank measurement to set the zero position of the readout system. So blank is always useful. And water is not always the blank. Remember that. Now, for the absorption, this is the typical component. So you have your encoder. Okay. It's similar to the luminescence spectrometer, except that all components are placed in the same optical axis. I don't know if whenever you put your cuvette, I don't know if you see in your sample chamber like an arrow. You can check whatever instrument that you have there, because sometimes your cuvette are what? Two sides are frosted, only two sides are clear. So if the students don't know anything, he might put the frosted one on here. So what will happen? Kung ito yung frosted, so the light will not absorb. And usually the reading that you have there, so instead na ganito yung baseline, usually makikita mo parang ganun. Right away, if you have been doing absorbance for a while, you're going to detect right away that there's something wrong in the reading. So it has the wavelength selector, monochromator, sample container, wavelength selector, that's the one selected by the photodetector, and then you have one that transfer your photodetector signal into a readable signal. So what you get here, transmittance. You can obtain the transmittance. So it measures the signal of the sample that results from the source radiance power passing through the analytical sample, and it measures also the signal from the references. So usually, may double beam pa ba tayo dyan sa LV? Buhay pa yung double beam?
Yung
So,
dati
wala.
po na double beam, sir, ay hindi na. May bago po.
Okay. Bagong double beam din. Because usually, kahit double beam dito, hindi ini-ignore namin yung isa. So when we blank subtracted, walang nakalagay. And then we put our own blank doon sa isa. Okay? So the way that you do, you get the signal from your sample and then the signal from the reference, and then you obtain the transmittance, which is just signal of your sample over the signal of the reference. Now, in practice, the presence of other signals, the dark signal, background emission, necessitates a third measurement, and that is what we call transmittance line. And this is how it looks like. Okay, E over ST minus E0 over E over R. So that is, we could say, standard and sample and reference minus the dark signal or every background emission that you have there. But we seldom have this now in high.
Bakit wala internet?
Okay. So if you're going to look at the signal that you have here, so this one, that's the total sample signal obtained with the source shutter open and the analytical sample in the sample container. Now E0T, that's a 0% transmittance. Now ERT, that's when you have 100% transmittance. I don't know, have you used the Spectronic 20? Hindi ba the way you operate it, you put something there and then you set it to what, 100? You still do that? So, ibig sabihin, hindi nyo na nagamit yung Spectronic 20. Because usually, what happened, you set it to 100. That's your, what we call blank. You set the transmittance there to 100 because 100 transmittance is equal to what absorbance? Di ba zero? So at least you have not what we could experience that practice. Because before, if we have the blank, we set the transmittance to 0. Okay, so yun yung ibig sabihin dito. And the 0, we could say 100 transmittance obtain shutter open and the blank reference in the sample. So any 0 transmittance there, we could say is just the background emission. So that's how we do it before. Okay. Mostly itong mga to, unfortunately, before it's useful on the principles on building the instrument, but now puro high-tech na lahat. Okay. So if ever what you're going to have here, the signal that you measure is really this, and it's a combination of all of this. The sample, okay, the emission coming from emission, the luminescence, the blank luminescence, and when you have zero transmittance there. And the way that we really look at the so-called true absorbance readout is this: the voltage, okay, divided by this what we call K prime. So if we're going to look at this one, this is the voltage proportional to analyte absorbance, and this is the log conversion factor involved in per unit, per A unit. So the voltage that we have here, and hence the absorbance, because that's really what it is, are found from these two measurements. So you have a reference logarithmic voltage or zero absorbance voltage, okay? You obtain it when the shutter is open and the blank is in the sample container. And then you have the sample logarithmic voltage that's obtained with the shutter open and the analyzed sample in the sample container. You don't do this now, but I experienced this time that yeah, I have to do this thing. Okay. And if you're going to look at the voltage that you have here, so you can get this reading, okay? Or we could say if you combine them, you have this thing. So you're lucky that you don't experience this thing anymore. But most of the instruments are designed following this what we call principle. So hindi nyo na na-experience isi-set nyo sa 100% transmittance yung blank nyo. Well, that's good for you. Okay? Because that means this is not applicable to you again. Because remember, this book was printed way back 1988. And even until now, they still use this book, okay, as what we call Bible. There's even no new edition of this book. I don't even know if those two persons are still alive. Bard just passed away days ago. So that's how you look at this, what we call spectrochemical measurement. So question. So the assignment that you have on Friday is to make sure you find the topic for your review paper and the journal article that you're going to critique. We're not going to meet. I have some deadline to finish. I just realized that I thought the deadline was April 1, and then I realized it's March 1. So I'm going to put something in the Google Classroom. You put whatever topic that you have there, okay? Para hindi naman magka-doble-doble yung topic ninyo, especially in terms of what we call article critics. So question. So I think the quiz, is it 2 quiz done? Because the third one is tomorrow. So I think everything is okay after I sent the same link doon sa dalawang quizzes. And then after you, what we called lost access to some of them. So question. So we're not going to meet on March 1 because it's March already on Friday. But as I told you, you have to spend your time to look for the article for you to critique and what is the paper that you're going to write.